Okay, this is the first lesson on the Group 2 topic, so we're looking at the alkali earth metals. And we're going to be going through this whole topic during lockdown, and it does lend itself particularly well to remote learning. There's a lot of things that we've come across before. There's a lot of things that we can hopefully build and develop on from what you know. I'll be doing the majority of the theory in this way, where you'll work through the booklet that you've been provided with and then you review your answers. But at the end of each session, I'm also intending to have a forms quiz for you to complete, just to double check that you've got some of the key ideas down and we can address any misconceptions that arise. But let's begin today's lesson by looking at the objectives for this topic. So we need to be able to explain the changes in atomic radius, first ionization energy, melting point, reactivity, and solubility of some of the compounds of Group 2 elements. And a lot of these you are already familiar with. It's only really the fifth bullet point that you haven't come across before, and we'll be doing that in a later lesson. I'm going to get straight on. I've actually said here as well, though, this does require you to apply knowledge. So as you're doing this lesson, can I really recommend, if you don't know the answer, go back to notes from what you've done to see if you can find help. Don't just go ahead to get the answer, copy it down, because what that doesn't do is deepen and embed that knowledge in a way that's going to help you to recall it and use it in the exams. So try everything before you go through and review. But let's have a look at task 1. Task 1 is prior learning, and we're back to electron configurations. And you've got 3 different elements here, doing the electron configuration in full and then doing it in shorthand. So pause. And when you're ready, we will start going through the answers. So for beryllium, beryllium has got 4 electrons. Now we hopefully remember that we go 1s2s in the order, and each of those holds 2. So 1s2, 2s2. Magnesium is 1s2, 2s2, 2p6, 3s2, because it has 12 electrons. And magnesium going up to 20 here, and we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But there's something that I want you to look out for on this. They all have a very significant similarity, and we can use that to our advantage when we're doing any electron configurations. So consider this a little bit of synoptic revision. I'm going to show you the periodic table, and on the periodic table I'm going to highlight the group that we're dealing with, Group 2. So we've got beryllium all the way down to radium. We generally are going to be dealing with the first 3 of these in the majority of questions. But I'm also going to add to this periodic table the outline of Group 2 and of the S block. And you can see the S block is over there on the left-hand side of the periodic table. And if we take a look at the 3 that we've just done, beryllium, magnesium, and calcium, they all end in S2. And that's because they are the second element in the S block for their period. The S block is too wide. The S sublevel holds 2 electrons. Let's take a look at a different example, and let's go to sulfur. Now you can work it out, and you can see sulfur has got 16 electrons, and you go 1s2, 2s2, 2p6, 3s2, 3p4. But we know it's going to end in P4 because it's the 4th element in the P block for its period. The P block is 6 wide. A P sublevel holds 6 electrons. I'm really hoping that pattern is becoming clear now. Let's do one final example to reinforce it, and let's look at vanadium. Now I can work out the configuration for vanadium, and I can say that it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. But I know that it's going to end in D3. And I know that because it's in the D block and it's the third element across the period in the D block. The D block is 10 wide. A D sublevel holds 10 electrons. And to finish off, I'm not going to do an example from the F block, but the F sublevel holds 14 electrons and it's 14 wide. So you've got a hugely important pattern there that you can come back to help you to double check and clarify your answers as you go. And now going back to the actual booklet, what you can see here, I have put in square brackets what the electron configuration is of the biggest noble gas that you can use, and we simply substitute that in. So you're not doing a shortcut at all with beryllium, but by the time you get to argon, the 1s2, 2s2, 2p6, 3s2, 3p6 can be simplified to Ar. Okay, moving on. What happens to the atomic radius as you descend group 2? Why does this happen? Now, hopefully quite straightforward, but pause, see what you can do, and we'll review the answer in a second. Okay, so I'm hoping that the what happens is easy and they get bigger. It increases. Why does it increase? Well, you can see from the electron configurations that in each subsequent element, you are adding an extra principal energy level. We've gone to 2s2, 3s2, and 4s2. So that 2, 3, and 4 relates to the principal energy level. We've got an extra 1 each time. That means the outer electron is further from the nucleus, and it's also subject to greater shielding. Okay, for the next task, I want you to take a look at the trend in melting points. I want to know the general trend for the melting point. Pause. And let's take a look. So, as I say, it's the melting point that we're interested in. And I can see from barium to strontium to calcium, it's going up, up, up. We're going to deal with magnesium separately in a minute because we are interested in the general trend. Now, you've come across this before. First ionization energy across a period has a general trend, but it also has anomalies. And we're having the same situation here. The general trend here is that as you go down the group, the melting point goes down. Now, why would that be? Well, the outer delocalized electrons are further from the nucleus, which means that they're more shielded. Or, sorry, it doesn't mean they're more shielded, but they're also more shielded because there are more inner electrons pushing them away. So the electrostatic forces that hold these metal ions together are weaker. And I think it's important here that we consider what stays the same in group 2, because all of them form +2 ions, so that has no influence. And all of them have 2 delocalized electrons per atom, so that has no impact. So the only influence on the melting point, the thing that's causing the decrease, is the fact that there is a greater distance between the positive ion centers and the delocalized electrons. So they're less attracted, less energy is needed to overcome them, the melting point goes down. And then we have a question here about the anomaly. We look, I've already touched on it, so we can see that it is magnesium. It doesn't ask you why, and you won't need to explain why. It's essentially down to having a different crystal structure, but it won't be something that you would need to explain in any great detail. Next task, pause, have a go at these. Now, definitions are the foundation to your learning. If you know the definitions, you've got straightforward marks you can pick up, but you also have access to the more difficult questions. So let's look at the definition. It's quite a big one, and you do have to be specific. It's the enthalpy change when 1 mole of gaseous atoms loses 1 mole of electrons to form 1 mole of gaseous ions with a +1 charge. And I've brought that up in stages to emphasize that we really need every component of that to have the definition perfectly. I'm highlighting some of the key bits that people often miss, but now let's put that into practice. And here's a perfect example of application. You know the definition, but can you actually do it? Well, magnesium goes from Mg to Mg+. It does that by losing an electron. And we've got the molar quantities there. 1 Mg makes 1 Mg+ and 1 E-. Similarly, Ca goes to Ca+ and E-. We're not doing what we normally do when we form ions, because we know magnesium forms +2 ions and calcium forms +2 ions. That would be a subsequent step that would take us there. First ionization energy definition is very specific. We've still not got the marks though. And it's down to one of the words that's highlighted. It's actually highlighted twice in the definition. It's gaseous, and the state symbols have to reflect that. So once we know the definition, we need to think about what the trends are. What is the trend in first ionization energy as you go down the group? And again, I think the trends here are far more simple than when we go across a period. So have a think about it, pause, and we will take a look at the answers in a second. Okay, so what we have in the first instance is a decrease as you descend group 2. And the reason why, and you're going to be getting a sense of deja vu here, the outer electron is further away from the nucleus. And if it's further away, it's less attracted. As I say, we are seeing quite a lot here of similarity to how we're explaining a range of different trends. So we can probably also remember that shielding is important as well. It's subject to more shielding, so the outer electron is more easily lost. Now at the next stage in your booklet, you'll notice there is a page for independent review. And I'm not going to ask you to do anything specific here. This is for you to highlight any mistakes that you've made so far, any errors, any misconceptions, or any questions that you still need to ask. The advantage of using this page and using it effectively is every time you revise this booklet, every time you review it, you're reminded of where your weakest points were. And if you can address them, that means you're going to do far, far better overall when you get to the exam. So moving on, we're going to look at the chemical reactions of the group elements. And we are told here group 2 reacts in a similar way, but less vigorously than group 1. So have a go at this, pause. And as I've touched on, the group 2 elements react in a similar way, but less vigorously than group 1. But the trend in reactivity is that it increases as you go down the group. Why? I did say deja vu earlier, we're into proper Groundhog Day territory. The outer electron is further from the nucleus, so it's less attracted. Remember, when these react, they're losing outer electrons. And they're also subject to more shielding. And so the outer electron is more easily lost. And we've got this really clear idea here that so many of the periodic trends as you go down the group, and there are others as well, we could think about electronegativity, that we can explain in almost identical ways. Remembering those similarities decreases the volume of facts that you need to learn. So understanding it is absolutely key. Going to move on with this to look at a model that you might apply. And I'm going to consider what might happen as people finish their A-levels and decide to go off to university. And obviously, you might be doing other things as well, might be apprenticeships, but I'm going to consider here specifically what might happen if two people who are thinking that they're going to be together forever, what happens if they both go to Manchester? One goes to Manchester University, one goes to MMU, one goes to Manchester and one goes to Bristol, or one goes to Manchester and one goes to Exeter. Now, you might need to look at a map here if you don't know where those places are, but why would I be talking about that in the context of this? Have a think about it, and I'm going to go through. Pause. Okay. So let's consider Manchester and Manchester. I mean, on the scale of this map, they're actually far further apart than they should be. But these two universities, Manchester and Manchester Metropolitan, are very close together. So you can see your partner daily, every other day. You can see them very, very regularly. There's not a great distance between you. And that also means there's less barriers. There are less people that you're seeing on the days that you don't see them who might lead you astray. So it can be very easy to maintain that relationship. Let's now consider Manchester and Bristol. And if I look at Manchester and Bristol, Bristol is about 3 hours down the M6 and the M5. Just in case anybody's interested in roads, but way down in the southwest. And so if you are 3 hours apart, you're not going to see each other in person every day. You might not see each other every weekend. You might be able to do every other weekend. But it's tougher. There's a much greater distance and it's harder to maintain that attraction. You've also, on those 2-3 week periods where you're not seeing people, got all of your new university friends who might be leading you astray, who might be trying to tell you that you shouldn't be wasting your time on somebody who's so far away. And so it's harder to maintain that relationship. And now let's consider Manchester and Exeter. Now, Exeter is a little bit further on, but the roads are terrible. So you're actually looking at about a 6-hour journey. In terms of every other weekend, it makes it much more difficult. Do we do once a term? Then you're barely seeing each other. The distance makes it so much harder again to maintain the attraction. And you've got all of those people around you being able to be the devil on your shoulder saying it's not worth it, stay here this weekend, don't go home. And it's far easier for that relationship to break apart. Now, I need to say, it's not inevitable if you go to different universities, relationships will end. It's just a model for chemistry. Okay, let's now try and rationalise it and bring the two together. So, Manchester University and MMU is by far the easiest to maintain the relationship because you're closer and there are less barriers. Manchester University to Exeter is hardest. There's a greater distance and there are more barriers. Now let's bring it to the chemistry. Beryllium might be Manchester and Manchester Metropolitan University. Magnesium might be Manchester and Bristol. So, in magnesium, the outer electron, the one that gets lost first, is closer than it is in magnesium, just like it's closer when you're both in Manchester. And there are also less barriers. There are less people trying to stop you going away for the weekend and seeing them. So, we're relating that to the shielding. Beryllium has got 2 inner electrons shielding and repelling the outer electron, pushing it away. But magnesium has got 10 inner electrons doing the same thing. When you combine both of those ideas, and you see that in magnesium, the outer electron is a greater distance from the nucleus and subject to more shielding, it makes sense that that electron is going to be more easily lost, and as such it makes more sense that magnesium is more reactive. Okay, that brings us to the end of part 1 of the Group 2 topic. Nothing actually new here. We're bringing together ideas from lots of different topics. When we get back to the live lesson, I'm going to share with you a Microsoft Forms, and that's going to have a few questions just to see how you've done based on the work today. So, any questions, bring them with you to the live chat if you haven't already put them in, and we will deal with them in there. Thank you for listening. Goodbye.